Okay, so the other thing that I wasn't able to cover in the tutorial was the topic of regular expressions. So regular expressions are these very nifty, I would say, tools, which I would sort of define as compact ways of representing regular languages. So this is a very important point. Regular expressions can describe or sort of have a compact description for languages, and these languages are necessarily regular, and all regular languages have regular expressions that sort of denote them or describe them, okay? So we'll see that in a second. I'll give the intuitive idea for why. But what's an example of a sort of compact representation of a regular language? So let's start with like a classic one. Let's take R is 0 plus 1 whole star, concat 1, concat 1, concat 0, concat 0 plus 1 whole star. So all of these things, this plus, this parenthesis, this Kleene star here, this concat symbol, all of these things are part of regular expression operators. So these are regex operators, operators. And a regular expression is built up by using atomic regular expressions. So atomic regular expressions are things like 0 and 1. So essentially, those are the regular expressions that denote the sort of atomic units in the language, in this case, the letters in the alphabet. The other atomic regular expressions are the empty set, or this is the regular expression that denotes the empty set. And also, let me write epsilon this way, right? So this is the regular expression that looks like epsilon because it denotes the language just containing epsilon, right? So we have atomic regular expressions. So if my alphabet is 0, 1, then those are 0, 1, the empty set, and this sort of epsilon thing. And each of these atomic regular expressions, you can think of them as sort of they point to exactly one language in the space of languages. So you can imagine like you have regular expressions, and then you have the set of all languages. Then one regular expression points directly to one specific language. So in the case of atomic regular expressions, it's very easy to know what they point at. So the way I like to denote regular expressions and the languages they denote is, R is the regular expression, and L of R is the language. So this is the language described or denoted or represented by. Note, regular expressions don't accept. So regular expressions are not language acceptors. They're sort of compact representations of languages. So the language described by R. Hello. So L of R is the language described by R. So in the case of atomic regular expressions, so if this is R, then L of R is L of 0, which in this case is just the language containing the string 0. L of 1 is the same for 1. L of the empty set is the actual language that is the empty set. And L of the epsilon, L of the regular expression denoting the epsilon string, is the set containing, or the language containing the empty string. Okay. And so, so those are atomic regular expressions, and you build up more complex regular expressions by using these regular expression, these regular expression operators to build up more sophisticated languages to represent, right? So how does that really work? So if we take this example, this is a good one, actually. That's why it's there. It's a good example. Okay. So if this is R, right? Then how do we know exactly what this is representing? So essentially what's going on is that there's a mapping between regular expression operations and language operations. So if you take L of R, right, what I can do is I can sort of break this down into multiple language operations. So here I would get L of 0 or 1 star, right? Concatenate, so now this is language concatenation. Language concatenation. L of 110. Well, that's just L of 1, concat L of 1, concat L of 0. And then we know, right? We know that L of 0 is the language containing 0. L of 1 is the language containing 1. So then this just represents 110. And then here I have 0 or 1 star on the right. So now this, so, okay, sorry, I was getting ahead of myself. Here, this regular Kleene star operation becomes the Kleene star operation for languages. So you can put it outside. And then this 0 or 1, the plus represents a sort of or. So in other words, L of something or something is that something union that something else, right? So that's going to be L of 0 union L of 1, O star. And then, like I said, L of 110, you can sort of break that down even further into the atomic L of 1s and L of 0s. And then you sort of get language concatenation. So let's do, yeah, why not? Let's do it. L of 1, L of 1, L of 0. And then the same thing for this guy. Oops, this guy here. Okay. Oh, I should have written the same thing. Okay. And then again, I can sort of, this becomes, you know, the set containing 0. So I'll just write 0, 1 whole star, right? And then L of 1, that's, you know, just 1. So now it's the language containing the string 1 concatenated with the language containing the string 1. So if you remember the language concatenation operation from tutorial 1, then this just becomes 1, 1, 0. And then it's the same thing here and here, right, in terms of the language. So this is 0, 1 star. And so now it becomes, now we can just recognize this as sort of language operations. So W in L of R, right? That just means that W is sort of broken down into 3 pieces. W is X, Y, Z, where X is from 0, 1 star. In other words, it's any string. Z is also from 0, 1 star. In other words, it's any string. And then Y is 1, 1, 0, right? That's the sort of subpart. So starting from this regular expression and using the atomic regular expressions, what they denote, and then using the regular expression operations to build up more complicated regular expressions, you can denote more complicated equivalent languages, right? So, so then in the end, what happens is, let's see, we started with R is 0, 1 star, 1, 1, 0, 0, 1 star. Then what we get in terms of L of R is, I mean, we can represent it this way, X, Y, Z, where XZ is in 0, 1 star, and then Y is 1, 1, 0. Or in other words, this language is just W in 0, 1 star, for which W contains 1, 1, 0 as a substring. okay? So this is the more sort of mechanical way of determining what L of R is from R, right? So R denotes a language, and this is sort of the brute force way, or the sort of brute force way, or sort of mechanical way of determining what L of R is. But normally, you just look you look at this regular expression and you think about its sort of pattern matching abilities, right? So 0 or 1 star, what this is telling you is that if I have a string W, right, the string W is going to match with R, right? It's going to match with R. Excuse me. It's going to match with R if, it has some string here, because this is telling you I'm going to match with a string that's any number of zeros or ones interchanged, right? That's what this regular expression is saying. So this is, any any sequence of 0 or 1s, 0 or 1s. Then what this regular expression then says, it says in terms of pattern matching, if W was to match with R, then it would have to have a 1, 1, 0 at some point, right? Because R is sort of restricting the fact that W must have a 1, 1, 0. So W has to have a 1, 1, 0, and then it can have anything else after that, right? So this is the more sort of quick way we tend to identify what L of R is. We just kind of think of the regular expression as sort of a pattern matching formula, and we think of what strings will match with R and which strings will not. Okay, and that's also super useful in terms of knowing how to design regular expressions. So in this case, if I want to design a regular expression that accepts the language, it's going to be, in this case, 0, sigma 1, sigma 2, W, sigma 3, sigma 4, where W is in AB star, sigma 1, sigma 2, all the way to sigma 4, those are letters. And I have the additional restriction that sigma 1 has to be equal to sigma 3. So this language then is strings, which, at least have 4 letters, right? They at least have sigma 1, 2, 3, 4. And the first letter of that string matches with the before last letter of that string, okay? So now what I want to do is I want to design a regular expression R, which denotes exactly L, right? So what I want to do is I want to design an R such that the language denoted by R is exactly L, right? The strings that match with R are exactly the strings in L, and only the strings in L, right? So there's a few tricks in terms of designing regular expressions. One big one is breaking things down into pretty intuitive sort of subcases. So this is, I would say, the first trick. Trick 1 is you want to just consider all cases. Okay. So what are the cases in this example? Well, I have that my alphabet is AB, and I'm saying that these 2 letters have to be the same. So there's only 2 choices, right? Either sigma 1 and sigma 3 are equal to A, or they're both equal to B, right? So I have 2 cases. I have case 1 and I have case 2. So I have 2 cases for string matching. When I have 2 cases, right, that means that I build 2 regular expressions, R1 and R2, and W is allowed to match with either R1 or R2. And this or, how is this implemented? Well, that's just implemented with this plus, right? So my regular expression R is going to be R1 or R2. Now I design the R1 for case 1. So the R1 for case 1, that would be the one where sigma 1 is equal to sigma 3 is equal to A, right? In other words, I have an A here and I have an A here. Here I can have anything. What does having anything mean in terms of matching? It means that I can either have an A or a B, right? The same thing for sigma 4. And then in the middle, I have some string W. W can be empty, or it can be whatever else you want. Well, whatever else you want, that's just W being represented by or matching A or B star, right? Because A or B star, that represents any possible string, because it's, any possible string is any sequence of A's or B's. So maybe it's this. Then what does A or B star say? It says match a string if each of its positions is either A or B, and that occurs any number of times, including 0, right? So that's what literally A or B star is matching. Okay, so then I'm ready, I think, to build R1. R1 would just be sigma 1 has to be A, so the first part of the regular expression is A. So this is sort of enforcing the strings to match to start with an A. Then I can have either an A or B. Then I have my sort of string that can be anything, so A or B star. Then I have my A again, right? Because sigma 1 has to match sigma 3. And then I have A or B. Okay. And then I just do the same thing for R2, right? So for R2, this would be B, A or B, right? So nothing changes except for switching this A for B and switching this A for B. So that's what I do here. And then this is the regular expression that denotes the, the regular expression being R is now equal to R1 plus R2. This is now the regular expression that represents the language I started with here. Okay. Okay, so that illustrates one design trick in terms of regular expressions. Another one, which I like to use, this is kind of an analogy to programming where you kind of want to do sort of defensive programming, but for regular expressions. So what do I mean by that? Let's add a bunch of pages so I don't have to keep doing this. Suppose I have the example here, which is I want to design a regular expression that represents the language over the alphabet 0, 1 this time, where W has no runs of ones of length greater or equal to 3. So what's a run of ones? A run of ones is just a sequence of contiguous ones, right? So for instance, if I have W1, 0, 0, 1, 1, 0, 1, then I have a run of ones of length 2, this one, and a run of ones of length 1, this one. So what L is saying is it's saying L contains all the strings over 0, 1, except for the ones that have runs of ones of length greater or equal to 3. So in other words, this would be okay. This would be an L, but something like this would not. This would not be an L. This is not okay. Okay, so how can I design a regular expression that denotes or represents this? Well, let's think of what I like to do sometimes. I like to think of sort of extremely long strings, and I like to see what the regular expression has to have to be able to match it correctly. So I know that W could have, a bunch of zeros at the beginning, right? That's totally legal. So zeros are totally okay, meaning that my regular expression likely has something like 0 whole star, right? Because this is saying, right, this has no restriction on runs of zeros, so I can have any number of zeros, right? Okay, now what can also happen, right? I can, of course, have a 1, right? I can have a 1, and that's totally okay. But I can't just say, okay, that means I can have 0 or 1 star, because all of a sudden what happens is I start to match, strings that have runs of length greater or equal to 3. So I definitely can't do this, right? So I have to play a bit of defense, right? In that if I have a 1, I have to make sure that it's accompanied by a 0, right? Because if it's accompanied by a 0, I know that I'm safe in saying, well, there's not going to be runs of ones if I have a zero right after. So for instance, what could be legal is, a one is immediately accompanied by a zero, right? That's totally cool, right? There's no risk there. So I'm also going to allow one and then zero, right? So right now what I'm matching is something like zeros and then 1, 0. Okay. So then I can have, a bunch more zeros. I can have, so a bunch more zeros. I can have another 1, 0. That's totally cool. If I have something like all of this whole star. Then this is saying runs of lengths, runs of length, runs of ones of length greater or equal to 3, right? Well, that means something like 1, 1, 0 is also okay. Well, if 1, 1, 0 is also okay, that means that, and why is this also okay? Because like I said before, I'm sort of, again, playing defense. I'm saying 1, 1 is allowed, right? I just can't risk having something like plus 1, 1 here, because then I could have, 1, 1 and then 1, 0. That could match with this expression. And then I would have 3 ones in a row. So that's not good. So instead, what I need to do is I need to place the kind of safety cushion. So I have to have a 0 as kind of a precaution. And that actually really almost about does it, right? Because now this sort of covers a lot of cases, right? I have a case where I just have zeros, that's legal. A case where I have, there's at least a 0 between every single one. So that's fine. Then sometimes things can get maybe a bit more intense, and I can get, maybe a 0, 1 here, then 2 ones here, right? But I'm never going to get the case with this regular expression of 3 ones, okay? So, I can have 1, 0, and then maybe 1, 1, 0. Okay. So this looks like it's almost enough. There's only now sort of a small piece missing. And so this is another sort of design trick in terms of regular expressions. You're kind of playing this tug of war between um, accepting too much and accepting not enough, right? So one design trick, so trick 2 would be this sort of defensive programming thing I'm talking about. And then trick 3 is you kind of want to play with false positives and false negatives. So play with false positives and false negatives, so that, sometimes you're going to be accepting too much, and so then you have to restrict the regular expression. Other times your regular expression is too strict, so you have to expand it a little bit. In this case, it's the latter, because now this all seems good, but if I have something like, I don't know, the string 1, or the string 1, 1, or even the string 0, 0, 0, 1, 0, 0, 1, 0, 1, 1. So anything essentially that's ending in 1 or 1, 1, that's never going to get accepted. And so what I need to do is I need to sort of add an additional kind of contingency, which is, well, I can have this matching, this sort of safety matching, but when I sort of see the final 0, when I see the final 0, I can either stop matching, or I can potentially have an extra 1 or 2 extra ones, okay? So that's just going to look like 0 or 1 or 1, okay? And this is the regular expression that recognizes this language. Now, the last thing I wanted to mention was at the very beginning of the video, I was saying that regular expressions denote regular languages and only regular languages. So that's actually a theorem which you've seen in class, which says that the set of all languages denoted by regular expressions is exactly equal to the set of regular languages. Okay. And so intuitively, how you can see this is you can build, so this direction, the reason for this direction is from a regular expression, you can build a DFA. or an NFA. Let's do an NFA. So for instance, if we take the example we started with, so R is 0, 1 star, 1, 1, 0, 0, 1 star. Really, we just have to sort of take the logic of the regular expression and map it to an NFA, right? So there's like a formal procedural way of doing this, but if you just want to do it quickly, that's really just the trick, okay? So the logic is that strings in the sort of equivalent FA should start with any number of zeros or ones. So what does that normally look like? Well, that's any number of zeros or ones, right? Then it's 1, 1, 0, right? So you enforce a 1, 1, 0, and enforce a 1, and a 0. And then I'm already pretty happy, and I can just sort of allow any other number of zeros and ones, right? So then this becomes my accept state, and I have a self loop because I'm sort of I'm taking the logic of 0, 1 star and having it here as well. Okay. So there's like a more involved way, which is like take epsilon transitions and connect everything together. That's in the lecture notes, but something you can also sort of use intuitive arguments like this. There may be one thing that I'm missing in this case is, if I had something like 0, 0, 0, like if I had or 0, 0, 0, then that's where epsilon transitions become useful. So I can say I epsilon transition here, or I epsilon transition to the FA that hard codes 0, 0, and 0. Okay. So there's sort of essentially intuitive ways of going from regular expressions to FAs, which tells us this subset equality, this subset inclusion. The other direction, that's essentially the K-path algorithm. I'm not going to do the K-path algorithm because I think it's a bit of a messy algorithm and it would probably be very painful. I'm just going to show you an alternative algorithm which you can use to sort of double check your answer. So you can use the state reduction algorithm. So the way the state reduction algorithm goes is, I have some FA, like in this case, this is a DFA, but it doesn't have to be a DFA. Okay, so I have this DFA here. Now, what I'm going to do is I'm going to create a sort of what's called a general transition graph. And the only difference between a GTG, so this is a GTG, and a DFA is that its edges can be regular expressions. So the immediate conversion is, well, the 0 as a string becomes the 0 regular expression, so there's no change there. 1, there's no change. 0 or 1, right? So this is, the logic is I either go to this state if I have a 0 or 1, so I can just encode that as 0 plus 1 in terms of regular expressions. And similarly for this accept state here. Okay. And now the state elimination algorithm, what it does, right, is it wants you to, the goal of the state elimination algorithm is to get, so the goal is to get to a GTG, a general transition graph, that has the start state, and then it has a single outgoing edge with some label R that goes to a single accept state. So that's the goal, right? So what I need to do is I need to eliminate states. I need to eliminate states that are kind of in the way. So I need to eliminate intermediate states. But of course, when I eliminate the states, I have to preserve the information, right? So for instance, what this would look like in this example is here I'm going to eliminate this state, right? So to eliminate this state, I have to think about, well, what strings are going through this intermediate state? Well, the strings that are going through this intermediate states are the ones that, they start here, then they have a 1, and then they have either a 0 or 1. So in other words, I can delete this state by sort of ripping it out. So I rip it out, and then I reconnect, I stitch together this transition with this transition, meaning that in terms of regular expressions, I just take 1 and I concatenate it with 0 or 1. And this becomes the label for this edge. Okay. So then remember, this is my goal. I want to work towards this goal. So now what can I do? Well, it kind of looks like I have some extra things in my start state and some extra things in my accept state. There's a few ways of dealing with this. One way is I add epsilon transitions because I want something that looks like this, right? I want something that looks like this. So I can just add epsilon transitions. For the start state, right? And another one for the accept state. And in this case, this stops being the accept state, and you get a new accept state here, okay? So now what the advantage of this is now I can rip out this guy and this guy using more or less the same method, right? So how do I do that? If I rip out, so if I rip out this guy, whoops, daisies. If I rip out this guy, then this becomes using the same kind of principle as before. Epsilon, concatenate. Now, what are the strings what are the strings that go through this intermediate state? Well, they start with the epsilon or the empty string. Then they have any number of zeros. In terms of regular expressions, that's something that looks like 0 star. And then they end with 1, concatenate 0, 1. Right? So that's 1, concatenate 0 or 1. And then you can do the same, right? You do the same thing for this state. So you rip it out, and you use the same logic, where in this case, I get this as the sort of start of my regular expression. Then this is saying I can have any number of 0, 1s any number of times. So that just translates to 0, 1 star. And then I end with an epsilon, right? And then this becomes the final regular expression. I can simplify a tad by just saying that R is then 0 star 1, 0, 1, 0, 1 star. Okay. And so this is like how you could run an alternative algorithm to check your answer with the K-path algorithm. Okay, and there's maybe like a few caveats, right? So what if you have multiple accept states in your DFA? If you have multiple accept states, make none of them accept states in a new sort of GTG, and just add a new single accept state with epsilon transitions. Okay. So that's how you handle sort of multiple accept states. And then the other thing you might encounter is, if you have something like 0, you have some intermediate state Q, and maybe you have sort of 0 or 1 here, and 0 here, 1 here, and let's say 1 star here. Right, so you can have, you know what, let's make this even harder. Right, so you can have something like this, ERT. And again, you kind of want to use the state reduction algorithm, but now if you rip out this thing, you have to consider all the possible ways that Q allows you to transition from pairs of states. So for instance, from P, I can use Q to go to R. So that means that when I rip out, so this is, step N. So step N plus 1, where I rip out Q. Then what I need to do is put this here. What I need to do is I need to say, well, I can get from P to R using Q. How do I do that? Well, I borrow this edge, so either 0, 1, then I go through any number of zeros, and then I read a 1. So then I can just write that down in terms of a regular expression. Oh, there's, yeah. And any number of zeros, then 1. I can also do the same thing. Q allows me to get from P to T, right? By reading 0, 1, having any number of zeros, and then reading 1 star. So I can get from P to T, 0 star, 1 star. And then this is maybe a bit more subtle, but I can also get from P, I can also go from P back to myself using Q, right? So I can read 0, 1, read any number of zeros, and read a 0 and go back to P, right? So then I add a self loop, which looks like 0, 1, 0 star, and then 0, right? And then I would just continue in this way, right? So this other caveat is just you have to consider all of the pairs of states that your intermediate state where you're ripping out is allowing you to sort of transition to, from, and to. Okay, so yeah, so hopefully that covers regular expressions pretty well, and you're more or less able to do all of the assignment questions related to it. So for the K-path reduction algorithm, this is more of a way of double checking what you're doing, and also to see if there's maybe a more simplified way of writing it out.